Hello guys, I welcome you all to my YouTube channel, and in today's video tutorial we're gonna see the gradient descent implementation to find the best fit line in linear regression, right? So first we're gonna see the three step that is most mandatory to find the best pair of theta, right? So first thing is to initialize the theta randomly, right? Second, to calculate the loss function. To see how good our theta is doing, right? And third one is to update the theta, right? Now let's suppose in a linear equation, in a linear line equation, we have something like this, right? Y equals to mx plus c. So what we are doing here, we are just taking theta 1 and theta naught instead of m and c, right? So here my theta pair would be theta naught and theta 1. So I'll be taking theta as the variable, right? Now if I plot the gradient descent curve for this, then it would be something different what we were using earlier, right? So it would be something like this. It would be a ball shape, right? Half ball shape, right? So here we'll be initializing theta somewhere here, and now we'll try to just converge at the minima. That would be here. So for that we need to update the theta naught and theta 1, and that will be doing using gradient descent approach. So what that gradient descent approach says to us, like you need to update the theta using theta minus learning rate and differentiation of loss function with corresponding to theta, right? And our loss function is y prediction minus y actual, right? And y prediction is uh, theta 1 x plus theta naught, right? So the loss function would be theta 1 x plus theta naught minus y actual, and the whole summation will be 1 by m, right? If we consider the x and y values to be the uh, to be of all the sets, right? Now if I do the differentiation of loss function with respect to the theta, then it should be for both the theta naught and theta 1, right? So for theta naught, if I consider uh, dj by d theta naught, then it would be okay. One thing I need to make clear here is that we will be using square of loss function, right? Because this loss function is not a differentiable function. Squared loss function is a differentiable function. I cleared that in the previous video, that if we consider the only the loss function, then it would be something like this. But if we consider the squared of this loss function, then it would be a convex curve, and it is also a differentiable function. So here we'll be considering the squared loss function, right? So this particular is squared mean error, right? Mean square error. So now the differentiation with respect to theta naught would be 2 by m, and here the theta naught will be 1, right? So it will, so we put the square to the minus 1 and we put 2 here, so it would be theta 1 x, or we can directly y dash into y actual, and it would be constant, so into 1, right? And dj by d theta 1, that would be 2 by m, and y dash minus y actual, and the here the theta 1 multiplied coefficient is x, so we'll multiply it by x. So we got the two gradient values that we need to update. So definitely what we'll be doing, we'll be updating our theta naught by theta naught minus learning rate into dj by d theta naught, right? And theta 1 equals to theta 1 minus n, that is learning rate, dj d theta 1. So this is how we're gonna update our theta naught and theta 1, and then we'll be calculating the best fit line that will converge at the minima, right? Now let's try to implement this whole scenario we have seen earlier. This is our training data. I'll just visualize this train data. So train.head is this one. These are the x values that is independent variable, and this is dependent variable, right? So let's calculate them. Train equals to train of x dot values to convert into numpy array. Y train equals to train of y dot values, right? So now the next thing would be to visualize these values. So I will be using import matplotlib dot pipe splt and plt dot plot plt dot scatter, yes, scatter, and x train comma y train, right? And plt dot show. Now as you can see, this data is not normalized. Then what we'll do, we'll first try to normalize this data. For that, what I'll be doing, I'll be just subtracting the mean value from the train value minus x train dot mean. I can apply this function because it's numpy values, right? And also I'm going to divide it with the standard deviation, right? Let's try to visualize. Now we can see the data is normalized, right? Now to implement the linear regression from scratch, I need 3 to 4 functions. First, I'll be taking the hypothesis function, right? And it requires x values comma theta, x and theta, that will be returning x into theta 1 and plus theta 0, y equals to mx plus c, right? The next function would be to calculate the updated gradient, right? For that, I'll be needing x and y and theta, right? So here, what I'll be doing, so in this gradient function, what we will be doing is we'll be just calculating these differentiation of loss function by theta naught and differentiation of loss function by theta 1. So we'll be calculating these values, right? And the thing to notice here is we'll be just adjusting this two value in the learning rate. So we'll be just calculating 1 by m y prediction minus y actual, and for theta 1 it would be 1 by m y actual minus y prediction minus y actual into x, right? So let's write the function for this. For that, I'll be just defining grade to be np dot zeros and 2, right? You need to import the numpy library for that, for sure. And the next thing, I will be calculating the shape, so that will be x dot shape 0, right? Now for I in range m, right? So okay, grade 0 would be plus equals to that would be okay. For that, let's calculate the hypothesis, or just name it y dash, that is the prediction. That would be hypothesis function, right, into x of I, right, and theta, right, and y would be y of I, so it would be y dash minus y, minus y, right? And grade of 1 would be the thing multiplied by x, that would be x of I, right? And in returning part, what we'll be doing, we'll just grad 1 by m, right? So I think these two functions are correct. And now let's write a function for update rule. Let's name it gradient descent, right? And here we'll be taking x, y, and epochs that I'll be considering 100 to be the first time for the first time, and the learning rate that should be 0.01 for now, right? Now let's define the theta to be 0 initially, np dot zeros 2 comma 0 2, right? And let's run the loop for I in range epochs, right? And for this, what we'll be doing, we'll be first calculating the gradients, right? So in this particular gradient descent function, what we are doing is we are calculating these two values, theta naught and theta 1, right? So we have calculated this theta differentiation of loss function by theta naught and differentiation of loss function by theta 1 in the gradient function, right? Now we'll be using these values and multiplying by learning rate and subtracting that from this theta naught and theta 1. So let's calculate the grade. That would be gradient function into x comma y comma theta, right? And now update the values. So that would be theta of 0 equals to theta of 0 minus learning rate LR into to grade of 0, right? And same thing goes for 1 theta 1, right? And in the end, what we will be doing is we'll be just returning the theta. Yes, I think so. So return theta, right? So one thing to see here, how can we see the error rate? So for that, we'll be writing a error function. So here, as you can see, our error is y prediction minus y actual by 2. So we'll be doing the same. So let's write an error function also. Def error. And in the error, what we are taking the x values, y values. That's all in theta. X, y, and theta. Right. So let's calculate the error. So m equals to np dot x dot shape 0, right? And in the next form, we'll be just iterating for. So error would be initially 0, e equals to 0 0.0 for I in range m. So e plus equals to y prediction minus y actual. So here y prediction is hypothesis, y prediction is these two values, right? Okay, let's substitute here. Now error equals to y prediction minus y actual and to the whole square, right? So here we'll be return e by m. So here we got the error function, right? Now let's update the error here. So we calculate the error function, we calculated gradient here, and then we updated the theta using the learning rate and gradient, right? So what we'll be doing here is we calculated the hypothesis function, then gradient, error function, and then we applied the uh, gradient to update the theta values, right? Now let's run this particular part. X is not defined in the gradient. Okay, yeah, that should be capital X. Now let's see the theta values. Error list, let's see. Okay, nan. It is coming nan, right? Maybe, and also we need to run it till 100 epoch, right? And all these are nan. Maybe there is some issue with the data frame. Let's check, is there any null values in the data frame? So train was our data frame is null dot sum, and yes, there is one null value in the y column, right? So for this, what we're gonna do is we're gonna just take the data frame and remove the row where the null value is occurring. So train and train y is not null. I think it should be working now. Yeah. Now let's see the shape of this train. Train dot shape. Right. Let's run all these values again. And here you can see the error is decreasing. Earlier the error was around 3300, and after that it start decreasing and it converts something else. Let's increase the epoch. Let's increase it to or increase the learning rate. Let it to be 0.1, right? Now you can see there is a drastic change after increasing the learning rate. The error reduced to 7, nearby to 7, right? Let's plot the error graph. That be plt dot plot, and here it would be error list and plt dot show. You can see that this is the error. Initially it was around 3000, and after that, after updating the theta every epoch, it decreases and it approached nearby to 0, right? Around 7. Now let's visualize the best fit line. If you see the best fit line, then we'll be using the theta values. Let's see the theta values. Theta, and these values are this: plt dot scatter x train comma y train, right? And plt dot show will give us the points. And now what we'll be doing will be just plt dot plot, and here we'll be giving theta values. So for that I need the x value and the y prediction value, that is y dash, right? So y dash can be achieved from here, right? Okay, perfect. So what we'll be doing, we'll be calculating the y dash, that would be hypothesis, and here I need to give x train and the theta value, right? And the plot, what I need to give is x train and y. So let's change the color of this. I think we are not able to see it because of the color to be red. Now you can see this is the best fit line, which is because we have the theta that is having the minimum error for all these points. Now let's check it for the test data also. So test.head test, we don't have it. Okay, have it for this. So our model performed well for the training data, but we need to check for the test data as well. So let's see. So test.head, right, and let's check, is there any null values in this? So test dot is null sum. We don't have any null values. So instead of this, what we'll be doing, we'll be just using the test data for this, right? So here it would be x test would be test of x dot values, and x y test, this is for matching the prediction value with the actual values. That's why we are using this test of y dot values, right? So instead of train, we'll be using test, and theta would be the actual theta which we have calculated earlier, and x test. We have not trained our model on this test data, right? Let's see it. Okay, we need to normalize this data as well. We need to normalize this. So x test would be, let's use the formula which we have used earlier, this one only. Normalization is must because we have normalized our training data, right? Let's see it. Yeah, now you can see our model is performing well on test data as well. So it means it is not overfitting, it's perfectly fitting our data. And this is the whole scenario for linear regression using gradient descent implementation. We have implemented gradient descent from the basic, from the scratch. Like we initialize the hypothesis. Hypothesis is giving us the y value for the new theta, and this is the gradient which we have updated, right? So this is the gradient, and for the gradient descent, what we were doing, we were just calculating the gradient from the gradient function. We are multiplying with the learning rate and then updating the theta as well. And in the end, we were returning that final theta, and that was the theta at which the error was minimum, right? And this was the error list. So it start decreasing, and then it approached something around 8, right? Earlier the error rate was not decreasing that much, but after increasing the learning rate, the error rate was decreasing very drastically, right? I hope you got the clarity about linear regression and its implementation from the scratch. You can also use sklearn linear regression library, but you need to have a vision about how to use it, like implementing it from the scratch and its mathematics behind that. Thank you so much for watching this video.